Hey, good morning. Good morning, everyone. Let's go ahead and, if someone could close the back doors, we're letting all the cold air out. So if someone could just shut those doors, I'd appreciate it. So welcome to the blended wing body session. And let's see, we've got 5 speakers. I see a handful of them, but I don't see Jimmy Ty, so maybe Jimmy Ty just walked in. Okay, good. Good. And I'm sorry about the last minute scurry here. We had a little technical snafu on slides, so we got that straightened out. And that was the first set. So this is a sort of a coordinated package that you'll see over the next few hours. Right up until about 12:30, I think. We've got Mr. Bert Guerrero from the Defense Department is going to talk a little bit about the project, how it fits into the Air Force objectives. Then we'll have 3 separate presentations from Jet Zero, who is our partner on this project. So the DoD and Jet Zero have partnered up on developing this full-scale blended wing body that you're going to hear about. And then we'll have Dr. Jimmy Ty wrap things up with a full system analysis, which the point of that is sort of an independent assessment of our basic goal, which is to demonstrate the L/D potential of the blended wing body at full scale, relevant Reynolds number and Mach number. So Jimmy will end the day with a very detailed assessment of basically our objective and how this platform performs against the reference platform. So you'll hear more about that. So first speaker is Mr. Guerrero. He's the sponsor of the project along with OSD, and so we'll turn it over to Bert to walk through sort of the overall objective, how it fits into his mantra, and then we'll go from there. Thank you very much.
Slide back and forth. I just click or? Yes, just use the mouse. Okay. All right. Let's see how that goes. Hi, everyone. Yeah, I'm Bert Guerrero. Some of these slides, if you were here yesterday, they might look a little repetitive, but that's just to kind of set the stage for everyone, understanding why we're interested in this technology, why we've worked with the Deputy Secretary of Defense of the Air Force, or of the Department of Defense of the United States to get this program funded. And then go into a little bit about what the presidential budget actually said about the program. I think it's pretty good, and Faye asked me to do this, but it's a pretty good description of what we're trying to get after. All right, well, maybe not that. So my office, just in general, I've been doing this for 10 years now. I'm a former aeronautical engineering student. In the 80s, I saw Top Gun 1 and said, man, I want to go fly for a little while. So I had a career in the Navy and the Air Force, flying a variety of different airplanes. Did some work as the Deputy Chief of Air Force Safety in reducing mishaps. And during that time, made some relationships between optimization of flight, which is a lot of process and technology, and how it relates to optimization of safety, which is a lot of process and technology. And the way I describe it is, you know, you reduce vehicle mishaps by having technology, anti-lock brakes, airbags, passenger safety through seatbelts, that type of stuff. The little alerts that you get now before you bump into something, it's all the technology piece. But at some point, you also have to appeal to the operator through driver training and whatnot to reduce the mishaps. So in the same way in the Air Force, we spend a lot of time, you know, on the technology piece, as well as a lot of time on the planning and execution of the mission and what the operator and what the operator's priorities are. So for us, you know, yes, there is a benefit financially for us, and in having more efficient aircraft. We burn less fuel. Yes, there's a benefit to the planet in that if we burn less fuel, we reduce greenhouse gas emissions for the same amount of mission that we execute. But for us, the bottom line, as the Department of Defense for the United States Air Force, is maximizing combat capability for the warfighter. So we're interested in developing technologies that allow us to go farther, stay on station longer, provide defense at great distances, and so that's why that we were interested in participating in this blended wing body effort. We have 5 goals here that I've listed. The energy intensity of operations is really just better efficiency. So sometimes that comes through drag reduction, sometimes that comes through propulsion enhancement. The second goal, no fuel, no fight. It's really important for us because we have a limited budget to make sure that we understand where our money's going and what the impact of that is to the warfighter. You know, how much benefit do I get? So that I make sure that I'm buying the right type of capability or the maximum amount of impact for the capability that I'm purchasing. And to be honest with you, that is actually not as well understood as you would think in the Department of Defense. The training and execution tools, the planning and execution tools were not as far advanced as I would have thought as well when I took this job over. So I'll just say that we used to do war games and we would not measure fuel very well. And it turns out in certain scenarios, fuel is the most important thing that we have to worry about because of the distances in the different missions that we do. Accelerate to win, and there's a quick picture of it, but there was a time where we would do mission planning on a whiteboard with dry erase markers and magnets for a very sophisticated, like I'm talking on the order of 50 aerial tankers, 250 receivers per day. And Eric Schmidt from Google visited that location as part of what we have called the Defense Innovation Board and pointed to the whiteboard and said, "What is that?" And so we quickly transitioned from whiteboard type of solutions, this was like 2017, to where now the majority of our planning and execution tools are automated. And then the second thing, and I mentioned this yesterday in my talk, is that we have less than optimal data collection on some of our legacy aircraft, F-16s, B-52s. We're getting better in next generation aircraft, 5th generation fighters, C-17. Even the KC-135 has pretty good data collection now. But that's key to really understanding how you operate and what you can do to optimize your operations through better planning and execution, as well as to understand the impact of the technologies that you're putting in. You know, does an engine wash really result in 1% engine efficiency and greater range or not? And then finally, we spend time publicly speaking about what we're working on, not only within the Air Force, but we're a member of what's called the Global Air Force's Climate Change Collaboration, GAFCCC is what we call it, which is 40 nations right now. I think it's 42 nations. And we share these types of stories just to make everyone smarter on what tools the various companies are using to provide more sustainable operations. So this is a little old data. Our number is actually much bigger than that now. Operational energy, last year's budget was close to $8 billion because the price of fuel has gone up significantly since 2022. And it varies, but at times it'll get up to as much as 10% of the Air Force's budget. And the Air Force burns more fuel than the Navy and Army and Marine Corps combined. So all the other military services in the United States burn less fuel than the Air Force does. So we're a pretty big target for efficiency, and so we spend a lot of time trying to solve that problem for our biggest platforms. KC-135, C-17, those are our big platforms. We want to make sure we understand better what technologies are out there and what that means to our ability to conduct operations around the world. This is what I was talking about. We literally had somebody in 2017 with very sophisticated schedules and a lot of phone calls, emails, just really not a way to run a 21st century organization. And so we've switched to this, and now we actually have an additional algorithm that runs in the background that gets us closer to 10 to 20% more efficient. So that's what we're doing in mission optimization. Power plant sustainment, we have put some work into various aircraft because we've seen in our collaborations with Delta Airlines and other airlines that there are ways to sustain our aircraft better than we're able to do right now. You'll see that in some cases, the initiatives that we go after are not as much focused in on efficiency, but efficiency might be a byproduct of something else that we're trying to get after. For example, the CV-22 that you see there was an aircraft that requires a lot of engine washes for maintenance. There was a lot of issues with dust and other particulate matter that was actually making the engines dirtier in their operations. For example, in New Mexico in the mountains, they do a lot of what they call brownout landings into mountain peaks. And so they had a program, but that program would require them to every so often open up the cowlings, actually open up those the two little bolts right there that were on either side of the engine. They would have to remove them and replace them with this engine wash detergent. That turned out to be a very maintenance-intensive activity, as well as you can see the one on the right, they would break off every once in a while, and now the aircraft's grounded. So we provided a solution that didn't require anything other than foam going into the intake of the airplane. And the operators and maintainers were pretty happy with that solution because that solution actually provided them with a quick way of doing that activity, reduced maintenance manpower by quite a bit. And oh yeah, it's great that our engines actually have a lot more power now at those high altitude locations. So that's kind of some of the stuff that we do. And the impact over the last few years has been on the order of, it's more than this, but just in these three big airframes, close to $100 million a year in fuel savings. So a pretty big number that we actually can recoup after the fact, and that's pretty important to us to be able to continue this investment. And again, you know, we have a lot of old aircraft. Some of them are going to fly past 100 years, so having different technologies in this way, drag reduction wise, are of interest to us. To include, we're doing some work actually with microtau on laminates, you know, tape, shark skin tape on the C-130 to reduce drag as well. Okay, so that just gives you a background on what my office does and why we're interested in drag reduction. So, so this is really the main part of why I'm here to talk to you all. So the Air Force has done some work in public-private partnerships in the past. For those of you who don't know, we've given a lot of money to Joby and Beta and I think Archer, as well as other companies, to advance urban air mobility. We call it Agility Prime. We thought this technology was important for our ability to conduct missions, not just in the Air Force, but in the Army and the Navy as well. However, if you go back to that earlier slide and you look at the amount of money that's spent, the Air Force, by and far, burns more than half of its fuel on the C-17, the KC-135, and the C-5. So our focus was, this is a great idea. This public-private partnership has resulted in, for example, in the 50s, and I think this was discussed yesterday a little bit, Boeing doing the Dash 80, and that Dash 80 resulted in orders from Pan American Airlines, as well as the Department of Defense. We had a competition in the Department of Defense between the DC-8 and the Boeing 707 and the Boeing 707-1, and so you had like 3 times as many Boeing 707 variants built worldwide as compared to DC-8s because there was this public-private interest in the technology. So, a few years back, we were asking the question about this, and we had had some discussions with the Chief Sustainability Officer in the Department of Defense on an interest in understanding what technologies were out there that we could support, but not completely by ourselves, because we couldn't afford to start a new program that way. But we felt like that that this technology, blended wing body technology, because we had heard of it in our previous interactions with Mark Page and his folks, we had heard that this was a possibility. So we had a competition with, there's a organization in the Department of Defense called DIU, Defense Innovation Unit, and their contracting mechanisms were favorable to this type of work, which is similar to what NASA talked about in the Space Act about setting gates for development of a demonstration aircraft. We initially set gates for a couple different competitors to show us their designs. We received those designs. We paid a certain amount to get those designs, and then the next step was we decided to go with Jet Zero because they had the best solution out there. And for us, the BWB configuration could make a lot of difference in our ability to deliver fuel at long distances, as well as deliver cargo at long distances. And the amounts were, in our studies, were pretty impactful on our various different scenarios that we have. And I'll read to you just kind of how this was pitched in the president's budget, because I think this describes pretty succinctly what the United States was getting after. This is the terminology that was used in the president's budget when we sent it over to Congress to get approved for this particular program. It says, next-gen large aircraft aims to accelerate prototyping and widespread adoption of blended wing body aircraft for military and commercial applications, leveraging common goals among Department of Defense and allied nations, commercial airlines, freight companies, and other industry partners and private investors. Cargo, tanker, non-stealth bomber aircraft account for approximately 40% of the Department of Defense's total annual operational energy consumption, estimated to be about 1.2 billion gallons per year. It's actually more than that. We're closer to 1.5. Next generation large aircraft endeavors to meaningfully reduce fuel delivery logistics challenges and prime the U.S. commercial aerospace sector to advance 21st century airframe designs in a similar manner as military developed aircraft primed commercial aircraft derivatives in the mid-20th century, which is talking specifically about the previous slide I showed you, the Boeing 707. And so the title said, Blended Wing Body Next Generation Large Aircraft Description in partnership with Defense Innovation Unit, allies, industry, stakeholders, and private investors. Next-gen large aircraft targets 30% increase in aerodynamic efficiency over traditional tube and wing aircraft designs using the same engines with a corresponding 30% decrease in greenhouse gas emissions. For military applications, initial analysis shows increases in combat capability greater than the percentage increase in fuel efficiency for both air refueling and cargo. In other words, you're going to get like about a 60% more fuel and or cargo delivered with a 30% increase in efficiency, and I'll explain why that is. Project goals include designing an aircraft that can cost-effectively scale up and down to enable acquisition by a broader community of government and industry stakeholders. Overall effort intends to manufacture a prototype large-scale aircraft for certification and testing. This project works in coordination with the DoD's Chief Sustainability Officer and the United States Air Force Operational Energy Office, which is what I run. So this is an example for us. In a big theater like the Pacific, if you're taking off from Hawaii and you're going out 4,000 miles, I can air refuel about 7 F-35s off the coast of Australia and maybe 1 F-35 in another location, like let's say off the coast of South America. So that for us really helps because, and this is in comparison to our current existing aircraft. So the one aircraft would be either refueled by a KC-46 or KC-135. The 7 aircraft is a blended wing body tanker. So it's a pretty big difference for us, and it really allows us to deliver a lot more fuel or cargo at range, and for the big theaters like we have in the Pacific, that's very important to us. This is our baseline, and we'll talk a lot more about this with the other speakers, but you know, our climate action plan calls for us to get this thing airborne by 2027. The aircraft technology demonstrator is intended to accelerate future options. So much like we say in the language, what we're trying to do is we're trying to prime the pump for not just more, for investment of other people's money into this program that would advance commercial industry interests that we could also leverage in the Department of Defense, because we just don't have the money to pay for all this right now. And the public-private partnership is similar to the AFWorks projects that I talked about earlier, which is urban air mobility. So we're thinking our initial investment will be about 1/3. Currently, I think the invested amount in the budget over the next 4 years was a total of $235 million of Department of Defense money, with another 2/3 by private investment and other capital. So that really is just an overview, excuse me, what our interests are and why we're interested in this one particular platform. You know, my office is about increasing combat capability. When we saw this, it was clear to us that this was something that we wanted to understand better and see if we could get commercialized. Thank you.
Okay, so we have probably 6 or 7 minutes for questions before we get started on the next segment. Any questions for Mr. Guerrero? So Bert presented the stakeholders' perspective. He's the sponsor. He's stimulating U.S. industry to move ahead with this project. We're going to hear a little bit more about how U.S. industry is responding. Any questions for the sponsor? Yes, oh yeah, here's one here.
Well, thank you for your very informative presentation. The blended wind.
Is that on?
Can you hear me all right? Is the microphone on? Yes. It's okay.
Okay.
My name is
Better.
Ranjan Banerjee. I'm from University of London. Blended wing body design, it's a brilliant idea. However, there is a however here. There appears to be some stumbling blocks. From my perspective, I am a structural dynamicist. I find the whole thing is so sensitive to pitch. Again, the problem with me as a structural dynamicist, I find it is difficult to provide sufficient pitching moment of inertia to this aeroplane. By sweeping the angle, you can achieve that, but it doesn't give you sufficient stability from the longitudinal point of view. The whole thing is too sensitive to pitch. Again, you must have, I'm sure you did think it through, but the problem is how do you overcome the stability problem of this blended wing body design? It may be a very naive question, but I'm sure you can.
No, not at all. I'm sure Mark will have something to say about this a little bit later. But let me just give you a little bit of background on trying to resolve that issue. So from about, let's say, 2006 to 2012, we worked, NASA and U.S. industry worked the X-48 program. The X-48 program had a B and a C, and it's very well documented in terms of what we were doing there, but it was a low-speed flight test. It was all about controllability at low speed of the airplane. We built 2-scale airplanes with Cranfield. We tested them in the 30x60. We delivered them to Armstrong, and the team flew those airplanes 132 times. 132 times. So X-48B went through its paces, envelope expansion, all the control laws. We had commercial pilots in the trailer, flying the airplane. Flew like a dream is what the final analysis was. There's a lot of technical data to back that up. But these guys are refining that design, and so they'll have additional insights into those refinements as we get beyond preliminary design, moving toward critical design. They start doing their scaled flight test program, their wind tunnel tests, and then their full-scale demonstration. So yeah, that is a ongoing challenge, but we do have history behind us in terms of being able to solve that one. So we're feeling pretty good about it. You'll hear a little bit more in the next hour and a half.
Well, thank you for that. You know, again, you have answered my question. My concern is the rigid body dynamics of the aircraft interacts with its elastic modes of deformation, and that interaction can be serious. You see, that is my main concern.
Yeah, okay.
But
So more of an aeroelastic.
Yes, I'm sure you have got a good story to tell, but
Yeah.
I look forward to hearing for the subsequent presentations.
Sure. Maybe we can get into some of those details in the next hour and a half. Any other questions for Bert? I see a couple of hands up. We got 4 minutes.
Good morning. Thank you very much. Joachim Hussen from South Africa, CSIR. I would be curious to know which alternatives were considered when you said the blended wing body was finally selected. Which were the alternatives that were also under consideration? Thank you.
So, I can't get into the source selection, of the different proposals, but there was a variety of different companies who provided, and some of them you saw yesterday if you were here when NASA talked about the transonic truss-based wing. They provided examples of other things that have been proposed in the past. I would just say that those are kind of the types of, double bubble. There were other platforms that were recommended, or at least were competing for this particular competition. And for us, the biggest thing was it had to be similar to a 767 in size, 767 KC-135 in size. That was important to us. It has to be able to take off from the same airfields that we operate currently in various different countries, in the Pacific and Europe and whatnot. And so that ended up modifying which aircraft we wanted to go after. So hopefully that answers your question. But other high efficiency aircraft designs that were out there, including double bubble, those were the types of things that were proposed to us.
And I'll just add, there was a series of X-plane studies that ran from 2016 through 2022 that NASA was running, and the DoD benefited from all of that work that we did. So we were running, small contracts, 6 months, 12 months in duration, for a long period of time, studying different configurations for commercial missions. And of course, what the DoD is looking for is a potential commercial solution that can be adapted to a military mission later. And so that focus on commercial solutions has been going for quite some time. Blended wing body research at NASA goes back to 1994. So there's 30 years of data, 30 years of testing, 30 years of study that these guys felt compelled to stand on as they moved forward. So it's not something that just occurred in the last few weeks or months or years. It's got a long history of research and development already. So we've kind of moved from that research mode into a product transition mode, which is, obviously that's a success story because there's a lot of U.S. government investment that's gone into that platform. And now we have a team that's commercializing, that concept. So we're going to hear more from them in just a minute. And so I think it's time to close off Mr. Guerrero's portion of this and move on to Jet Zero presentations. And we're going to see 3 of those over the next hour and a half. I think we're going to start with Scott. Is that right?
I think Mark's the first.
Okay, we'll start with Mark. So we'll turn it over to you, Mark.
Thank you very much. Thank you, Faye. So lots of familiar faces in here. It's great to see you all. Okay, let's see. I think this button should advance the slides, right? It sure does. This all started with a question posed by Dennis Bushnell at NASA that prompted a number of responses from industry, and the one that Douglas offered, Dr. Liebeck and crew, really caught the attention of Boeing, really got the attention of NASA. And that is how this whole thing got started. It wasn't organically in stewing around in the different companies. It wasn't. It was really the question saying, what else can we do besides tubes and wings? The first contract, actually Dan Golden, who was the NASA administrator at the time, he came to Douglas to see what we were doing on research. We put up all these slides showing all the stuff. We had a curve that was lifted drag ratio versus year, and all this stuff and all the technologies that were being described. Then boop, up here in the upper right-hand corner, there was a little bug, a little black thing. He said, "What's that? I haven't heard about that." That was a blended wing. So even after that initial start and the interest in that possibility, it wasn't industry that was propelling it, it was NASA. And with that, we started looking a little bit deeper. But we were seeing numbers in the ballpark of 25 to 30% fuel savings. Then we started looking at everything in great, great depth. Again, this was NASA sponsored, and it was a joint activity between Douglas Aircraft, NASA, and 4 universities. And we had to split that $3 million all the way around with everybody. So it was money efficiently spent. But we got to build all the things you would expect in an R&D program as it matures. Get a FEM model, get the CFD in hand, look at the flight mechanics, and then size it for a mission that would be economically competitive against other aircraft in that class. And there's the airplane. So that's the one that was, you can see it has boundary layer ingesting inlets. They're mounted to the top of the airplane engines, and the body flow goes straight into those inlets back then. We and others have moved away from that. But this one was really getting down to the integration. You can see in the picture in the upper right there, those are the landing gear door apertures. This was a giant airplane. So underneath the cargo, we could put landing gear. Airplane was 2 decks of people, 400, 400. So it was very challenging to find a place for landing gear, in this case, that was narrow enough to fit on modern runways. So immediately we saw that pressure vessel was going to be a big, big challenge. And the reason is really simple. If I have a pressurized cylinder, we all know I get hoop stress, and hoop stress is just tension in every direction, uniform. You're not looking at buckling, you're not looking at all kinds of things that are hard to do with a laminated structure. But since we had a flat top and a flat bottom on our pressure vessel, when you pressurize that, naturally you're going to get interlaminar shear, and that plays a role along with the peel stress to shorten the life of the composites. We had to fix that. And there was an amazing study started by NASA with Dr. Alex Valicki, who had a concept for how to build a fuselage. It was called Perseus, protruded rod, stiffened, efficient, unitized structures. And the crew at NASA, Langley, worked with Boeing, and they got an amazing package, an amazing test program, very massive load introducing piece of equipment called Colts that was at NASA. And then Boeing built that fuselage, which was actually about 85% scale, but it was 2 decks, curved and flat surfaces, and put it all together, pressurized it, cut holes in it, did all those things, see where they were. It was just a stunning success, because the thing that was needed to address these interlaminar shear issues and, of course, peel stress was stitching through a dry stack laminate and then resin infusion. And when you do that, you've hit right at the heart of the limitations with most composites today. But the other thing that was interesting was that stitch line, 100% every time, was a beautiful crack arrestor. So when you look at the 2-bay crack, where they take your beautiful structure and they cut a little slot in it between 2 bays defined by stringers and ribs, the boundaries, and cut across, let's say, a rib that way, cut across a stringer that way, load it, and make sure it has at least a safety factor of 1 at The design limit load factor doesn't need to be 1.5. If it does, then you've done it, and they did. Around that same time, I had founded a company called Design Technologies that's still out there doing great, and I retired from that to found this company with a bunch of stock I gave back to buy out the work that we had done at Design, again under NASA sponsorship. So the thread really was continuous. I was working with colleagues at Douglas, getting the whole thing going. I go off and do crazy race cars. I go off and do the drone world, and then ultimately come full circle right back here. So the folks who've had a hand in it, there's been a lot of continuity. And NASA was the central piece that kept it all going. So this is one of those X-Plane programs. And what happened with that X-Plane program was Design was not a big company. Jet Zero was getting bigger fast. But we were asked to actually put together an entire program plan that withstood inspection by NASA. They asked for a thing called schedule-infused, or something. Risk-infused, there you go, thank you. The whole idea of that was you put a schedule together, you identify all the nodes that are critical path nodes, then you do a Monte Carlo analysis of all the possibilities of where you could have the kind of failures that you've had in the past. You get the 80-80, 80% certainty, 80% certainty on cost, 80% certainty on schedule, and that's what we had to work to. That was the foundation of the work we're doing today. We took that exact same kit, grew it again, so it was 100% directly applicable to getting here today. So, but that X-Plane program changed directions, ultimately became the truss brace wing from our buddies up at Boeing. So, just summarizing, we started first with the bug in the upper corner of the presentation by Douglas. Dan Golden said, "What the heck is that? I want to learn more about that." And then he said, "Tell us more." And we got started. This is that little $30,000 contract. We evolved it one step more. You can also see here this had a mail slot inlet with boundary layer ingestion. Then the big program resulted in this airplane. This airplane was comprehensively worked on. It had a very substantial amount of analytical work on that, especially in structures, flight mechanics. But the other thing is that's when the wind tunnel test campaigns really got it going. In-ground effect, out-of-ground effect, low speed, and transonic. And then after that NASA program, Boeing started looking at where they would go next, what they would recommend next. They took it down from 800 passengers to 450. 800 passengers is a lot, but back in the day, we were slot constrained. And everyone thought the only answer was going to be bigger airplanes in those limited slots. So airports have a certain number of gates, a certain number of slots. Slots are on time scale. Gates are just spatial. How many do I have to park things at? So it looked like the only solution was to go way bigger because airports weren't building extra runways to increase the number of slots. Your runway you can't change your runway itself to have much of an effect, but if you put on another runway, you've just doubled your slots. So 2 airplanes can arrive at the same time instead of 1. That ended up changing very fast. The airports did invest in adding runways and solve that problem. And by the way, that problem was also instigated by the hub and spoke system, which we all think of as that's travel today, but it wasn't always there. Someone finally realized that I can go substantially, I can take an airplane maybe 45 degrees off of the straight line to my destination, land somewhere, refuel, and go again to finish up that flight and have burned less fuel than if I had done a straight line flight. And once you have that realization, the folks at the airlines go insane because they can completely optimize their network and their scheduling. And then later again, Boeing started looking at a twin engine, blended wing. Still, this one was again a bit smaller. This was about 250 packs. This became the core of a lot of the NASA-sponsored work back at that time. I'll show you a little bit more. And then this was also about the time that I had left Boeing in 1997, formed this crazy company, got some NASA funding, and now spun that company out as Jet Zero. But what we were doing back at design was the Ascent 1000, and our thinking was to do a disruptive attack from below. Don't go to Boeing head on. Don't get bombarded by going head to head with Boeing and Airbus. Go underneath them. I have to go head to head against Gulfstream, which is the challenge. But get that airplane going, mature its technology, take the fancy interior out, put these seats in, and believe it or not, those two missions of a 737-7, let's say, or maybe a Dash 8, and a BizJet, they need the same they need the same useful load, but they get it very differently. BizJet has a bunch of useful load in fuel, the commercial jetliner in the payload. So we worked that. That got some NASA sponsorship, and then finally, in about actually for us it was 2012, but later then, 2014 and 2016, we got caught up with NASA, and they were interested in a particular area we were working on. And that was that little small blended wing there, the BizJet. That one had to be single deck, not double deck like all the ones before. Everything to the left of that, those were all double deck airplanes. People over people, or people over cargo, like tube and wings, right? So it was a challenge to figure out where to put the landing gear once again. But there was another challenge. This is a swarfy, curvy airplane. How do you grow it? How do you make an airplane? 737s or A320s can go A318, A319, A320, A321 on the same basic platform. Sometimes that's the same type certificate, and all those changes only come with an amended certificate. But certainly within each model, you want a couple, 3 airplanes that can be operated really efficiently. And the reason for that is that the airlines need a family. The reason they need a family is because they know we can do simple things like just increasing the capacity of that airplane, live with a non-optimum wing, live with a non-optimum tail, all those other things, but this is so inexpensive and so straightforward that this has become the worldwide model for all of aviation. This is what we do. This is how I plug an airplane. And the magic is, how do you make that right-hand airplane still work when the wings are no bigger? Usually they just up the engines. That's how you do it. Bigger brakes, bigger engines, and makes up for it that way. But the real limitations, but you could see the motivation with an amended type certificate. I don't recertify everything. I focus on the stuff that's new and its influence on other things that were before it, of course. And then you also want to get a common type rating. That means that across, let's say, 3 airplanes, 757, 200, 300, whatever, that the pilots would not need special training for each one. They could jump into each one, left or right, up or down. And again, for the airlines, schedulers, this was huge. The ability to have a common type rating across usually what's about a 30% passenger capacity range with a tube and wing aircraft. You can save a bunch of money on NRE, you can save a bunch of money on tooling. Sometimes these airplanes were built, they just maintained the rate by putting the new wings into the same jigs, and they just had a gauge change between the frames and stringers and ribs and, frames and longerons, ribs and stringers. On metal airplanes today, I think most of you know this, but if you have a fuselage with a big curved piece of aluminum and it's acid etched, the first thing it does is goes into an acid bath to set the gauge very precisely between all of the pads where the stringers and the ribs and the frames are going to intersect. What that does is, in those little lakes in between that have been etched out a little bit, I just leave it, put some back, put some back, put some back. The tooling to assemble it doesn't change. All kinds of things stay the same. You just beef it up a little, and it's a beautiful process. The challenge, of course, is that, as you see, if you make the airplane big, 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 when you stretch it, you're kind of running out of wing. And so we know what happens. Takeoff field length is really bad. You put a bigger engine on, only helps so much. The lift-to-drag ratios are penalized, all those things. But this is still the straightest path to a more efficient occupant of that size of an airplane. Okay, how do you do a blended wing when it's all swarfy? Well, we've got this problem that we have three-dimensional curvature all over this airplane, where if I just cut the nose off alone, obviously nothing good is going to happen. But we have this thing called a Y-plug, the blue part. And with the Y-plug, we're able to shrink down and up from a center airplane, or start at the smallest one and stretch up, but always designed with the knowledge of the brothers and sisters in the family. So when we're doing optimizations on this airplane, and we're starting with the middle of the market airplane, we can go down into twin aisle, we can go up into twin aisle, we can go down into single aisle with that same cockpit assembly, the same outer wing engine and so forth, fuel tanks, and what I add in the middle is really pretty simple stuff. It's mainly just floors and seats. Bigger ECSs, of course, but the thing that's interesting about this that we and the industry are just getting our heads around is that a blended wing can more than double its capacity from the left end to the right end on the same type certificate. Have an amended type certificate in between. That'll test the FAA, but technically the airplane looks so similar in terms of its ability to manage the CGs and to keep the aero center aligned that it's wonderful stuff. That was a big enabling technology. And the other thing you'll notice is we still have the engines intimate to the top of the airplane. A lot of blended wings do have pylons, and pylons are great because they ensure that you don't have mutual interference, and they ensure that the air going into the engines is completely clean. We do something different though. We have a diverter. If you look at the diverter at the bottom here, so it's just like a diverter on an F-16 or some other airplane. I don't know if I can make, there we go. There's the diverted stream. Well, look what it's next to. It's next to a high velocity fan jet. So when I have high thrust over airspeed, thrust over dynamic pressure ratios, it's sucking. It's pulling all the muck in. The slow moving muck gets pulled preferentially in compared to the fast moving stuff because that has too much momentum. It can't turn the streamlines. So we have a vacuum cleaner at high power that keeps that inlet pristine. Blended wings, when you take them up to stall, the wing stalls first, usually near the kink in the middle, goes outboard, and it doesn't go inboard. The engines never see airframe wake, true wake entering the inlet, even on this, until 10 degrees past CL max lift. So this is a key part of getting rid of more weight and drag. And it might not be obvious, but if I have a nacelle, pylon, and body airframe, I got a pylon, there's left and right surface area. I got a nacelle, there's all that surface area. When I do this, I put it down, I erase the shadow area under the nacelle. That friction area is gone because the ducts there are designed at cruise not to pump hard, but to actually compress all the way but down. So the average velocities in the duct are very low compared to free air. So we get a very substantial drag savings from getting away with less friction drag underneath the entire nacelle, less friction drag underneath the shadow of the nacelle that would have been there on the wing, and complete elimination of the area and weight of the area of the pylon. The pylon still exists, of course. It's just left and right supporting this arch structure. So this was a surprisingly important part of the benefits in terms of evolving the airplane beyond where we had in prior instantiations with NASA. Okay, you've heard 50%. That's a big number. It's not always 50%. Sometimes it's 43%. Sometimes it's 45%. But a lot of time, the airplanes that we are replacing, it's 50%. So that's exciting. Airlines would love it. Does it integrate with airports? Yes, it does, because it has to. So we had to design this so a regular jetway could use it. We had to design this so that the cargo belts still fit and the sill heights still matched or were close enough. We have the potable water, the wastewater, the refueling, defueling, all those things are very conventional, actually. The airplane looks different, but frankly, there's virtually no change. In terms of the cockpit development, we're moving way fast on that for the demonstrator. But it's a sophisticated, modern, quad-redundant, beautiful display cockpit because there are those things that already exist today. And we didn't want to burn off the efficiency of the airframe at the altar of more electronics that are more modern. So we're intentionally freezing hydraulics, electronics, and all the other secondary systems to now. So the systems that we're going to put on demonstrator, most of them we expect will be on the product. So we heard a little bit yesterday about these airplanes. You got a lot of stuff to do. You got SRRs, PDRs, CDRs. There's a lot of stuff to do. But somewhere, someone is actually making relationships with the suppliers and getting them to sign a contract. So all of our stuffings have been sourced. Everyone's ready to go. Probably 2/3 of it are under contract already, including the Collins displays that you see here. We have an amazing space that we can grow into for many years. And that was possible because of working closely with Long Beach, the mayor's department, and so forth. We found a way where they could keep some stuff that they always wanted, and we can get some stuff, and ended up making really a transformational investment in us, so that we probably got that property for 5% of its actual value. On the right, you can see the interior mock-up. That's a big deal because this interior is so different. You're going to hear a little bit more about that from Scott. And then we have the integration test facilities all getting populated around those ones. So airlines are taking notice. Alaska has announced. We also just recently had the announcement from EasyJet, but we're actually on the path to getting these other partners committed, usually in the form of reserved positions, not yet orders, but reserved positions, and also getting their investment arms plugged in. And there's quite a number of those. I think before Christmas we should probably announce 3 more airlines, major airlines. So these are the folks who are providing the equipment that's going to go into the demonstrator and also the real airplane. As I said, when we've put these out for quote, they've worked both problems. What does this look like on a certified airplane that's going to fly forever? What does this look like just for this outing? And we found the latest technology, pre-certified and compatible across the different subsystems, and that turned out to be hardly a problem at all. I really thought we were going to have tons of problems disassembling everybody else's airplanes, taking pieces from 5 or 6 different airplanes and putting it back together. That's been surprisingly seamless. So we're blessed with an absolute, we've got a bunch of angels over us watching out and holding our feet to the fire. You can see right beside me, Tom O'Leary. Tom O'Leary was the piece of the puzzle for me that's been missing. Tom O'Leary is our CEO and my co-founder. And until we had that type of skill set, on top of all the NASA support we'd gotten and interest we'd received, we had to have that piece to find a way to make this happen with the investment side of the world, not the production and profit side of the world, all investment. So he's done an amazing amount. Next to him is Rob Dewar, a father of the C-Series and the A220, came to us straight from Airbus. And there's all kinds of folks on there. You can see Dr. Liebeck on the bottom next to Preston Henney. He was executive VP at GM. We have Brian Barents, who was at Cessna. He was CEO of Aerion, and Learjet. And believe it or not, he did a stint between BizJets and went to Japan, where he and Dr. Toyota were going to make a new car. He said, you have to have a new brand, not a new car. And that was Lexus, and I think he picked the name that the other guys figured out. And then Barry Ecclestone, bottom left, big part of the V2500 program. So I will now pass it to Scott, unless we want to do any questions now, or if I plowed through. Okay, cool. Thank you, Mark. You bet.
Let's take one question for Mark before we transition to Scott. Ricky.
I think I'll just start with a question. So you've actually put a lot of emphasis on the engine, right? Have you, that's excellent for design conditions, but have you actually thought about off-design conditions like crosswinds and issues relevant to this? I guess it's a bit, well, it's a bit, you're a bit,
It's
a bit down the line.
Yeah, you're right that the off-design conditions are always the interesting ones. For us, we have a strange set of circumstances. We got this big top surface area. Yes, water's going to collect there. Yes, some snow's going to collect there too. But interestingly, once I rotate the airplane, do a mission, land, and when I start derotation, the airplane is self-shielded, so birds and hail can never hit the engine. They can barely, they don't even hit, they skim a little bit off the nacelle, but it's like an inertial filter. It's sort of like a vortex filter because the streamlines can't turn as fast. The water droplets can't turn as fast as the streamlines do. So that part's really cool. But the off-design condition in crosswind is one of the most interesting. So the airplane turns the flow into the engine at all flight conditions and never stalls. So there's no upwash, downwash issue on the engines. And engines today, you might not be aware, there's so many tens of thousands of pounds of lift on those inlets when they rotate today on all of our airplanes. That load deforms the fan case, and it's a big part of what limits how tight we can do sealing. Some airplanes have had the experience where after about 3 flights, they've already lost 1% of efficiency because of that deflection. So this is something that doesn't happen, but crosswind does. And the standing vortex that you sometimes see form like on different aircraft, it is there if I have a little crosswind. That will be there, but it's also on every airplane. People probably don't appreciate that even the C-17 with the engine so high, right? You've got those things, standing vortex. And the every T-tail engine, T-tail airplane with twin engines at the back, they also have standing vortices going into the engines virtually every time. You don't see them that much, but so it turns out that that's not, it looks scary, but it's not actually not a problem. The total pressure losses are very low.
All right, I'm going to take 1 minute of Scott's time, Mark, and give you 60 seconds to tell the crowd, how do you know all these things? What are you doing at Jet Zero to resolve questions like that?
So we have great partners, and we're building great capability inside the company. For example, the crosswind work that we were doing on the inlets, all that CFD was done by Northrop. And their engine guys were looking at it, and they were looking at the total pressure deficits from some crosswind conditions and assessing those. They've been a great help. But we have this huge volume of data built with the NASA investment over the years. So we have a lot of the toolkit available there. And that's been a big thing.
And you also have your own in-house CFD team.
Absolutely.
That's run many thousands of iterations over the last, what, 2 or 3 years?
Probably, yes, I'd say that a lot more than that. But so yeah, we have, obviously we have our own CFD capability. We're doing our FEM and the manufacturing simulations. We're in the process of imminently selecting the factory location. We've been dancing with 16 different locations. We know that down to 7, and I think we know which one is going to work. And they're lining up, and of course they always want to give you $2 billion or $4 billion, but our guys say you're going to get $6 billion before you're done. So we're not going to say yes until they offer us $6 billion. That's just the price of doing business these days. Great for us. So that's really underway. I'll tell you one cool thing. Some of you guys would really appreciate. Dr. John Basberg, he was one of the most senior aero guys at Boeing, and one of the very first person to do a transonic solution on a blended wing. He and the CFD team have created a capability to morph the airplane control surfaces with sharp edges and gaps without doing a giant regrid. It's all automated. And so we can do an entire air data report, CFD only, entire air data report in about 7 days. Everything, pitch damping, yaw damping, control mutual interference, ground effects, all that stuff. It's amazing. So
Okay. Let's end it there, Mark. And we're going to turn it over to Scott and give him his 30-minute slot. But you might get some more questions. Are you coming back up?
I will be.
He is, right after you, right? Right. So we're going to take 30 minutes to hear from Scott, Chief Product Officer at Jet Zero. Then we're going to turn it back over to Mark.
Thank you, Faye. Good morning. I have the wonderful opportunity to talk to you about how this amazing new technology would apply to the commercial market. And, you know, part of our contract with the U.S. Air Force, thank you, Mr. Guerrero, is to develop the full-scale demonstrator that'll fly in 2027, prove the aerodynamic performance of the aircraft. But the other piece of it is the Air Force is catalyzing our development and investment into the commercial aircraft. And so when we talk about a commercial airliner, we're really talking about a product that a company wants to buy, a product that people want to fly. Airlines being the companies, and they want to make money, and they want to be more effective. And the people are passengers and crew, and they love to have a better experience in what they enjoy. The good news is the future of aviation is taking shape with this aircraft. And I showed a little bit of this yesterday if you didn't get a chance to see it, but remarkably, from man's initial desire to fly through the first 60 years of aviation, we had amazing airframe innovation. And eventually we settled on a couple, on a form that became really the dawn of the jet age. And man, has that aircraft served us well. It's literally transformed the world into the place we know today, and probably why many of us were able to get here for a conference like this. The challenge has been over the next 60 years, we're still in the same basic airform. Not without innovation and advancements, but basically the same tube and wing aircraft. And the challenges of 1960s are not the same as they are today. When we look forward into what we need to do, we need to continue to drive efficiency gains to keep the cost down in the industry. But efficiency also translates to fuel burn, which translates to environmental performance. And we absolutely have a challenge to improve the experience for those who fly. When we look at efficiency, this is not where you want to be on a learning curve at the very bottom, right? And this is fuel burn efficiency, directly correlating to the most significant cost that commercial operators face, which is fuel, and also the most variable. And as that is leveled off, the airlines have had to go to a little deeper in their well of tricks and figured out how to optimize the cabin space as well. Okay, I see you've all felt this. An aircraft that was developed for 150 passengers decades ago at 70% load factor before we had roller bags to bring on board, now holds 180. And by my recollection, it's always full. I'm sure you've had similar experiences. And so this puts a lot of stress, not only on the airframe, but the crews that fly. The airlines aren't doing this to line their pockets. They're doing this because they have to. They're keeping costs down for the flying public to keep the demand up. And the margins of the industry are not, I would say, overly robust. And even a bunch of good years can result in a single event that wipes out a decade's worth of profit for the industry. And so in many ways, it's not easy to be an airline. They're kind of hanging on by their fingertips, right? The best can make single-digit profit margins. The challenge in front of us, though, is magnitudes more than COVID, which has a massive impact on the industry. The challenge of net zero, by some estimations, is $4.6 trillion of investment, predominantly in sustainable aviation fuels, SAF, but also in hydrogen electric propulsion. That investment is before we even consider a 2 to 3 times increase in fuel for SAF in an industry that can barely eke out a profit today. And so while we're big fans of all the investment and a lot of the technology we've seen today, we'd like to throw another piece into the equation here. a much smaller, magnitude smaller investment into a new airframe that's more efficient. And that step change in efficiency will have an impact as soon as it flies, with up to 50% less fuel burn and emissions. As Mark noted, the efficiency numbers we're talking about are literally only from the shape. The shape is delivering that improvement. It is the new technology. And so as we look forward to the next 30 years, and we understand that we have environmental challenges and cost challenges, if we zoomed in on that learning curve, how long can we stay on this same curve? Can we continue to eke out incremental improvements that take a vast amount of resources to make 1% or 0.5% difference? Or do we jump onto a new curve? And this is what the blended wing body represents for the industry. There's a chance to now make a leap forward simply from the airframe, an airframe that will benefit from any new propulsion systems that come along. But when it enters into service, we'll deliver up to 50% less fuel burn out of the gate on typically the aircraft it'll first replace. Now that learning curve has a lot of implications when it comes to the airlines, but probably the simplest one is when we look at both the emissions from Jet A and the fuel cost, we know that SAF will lower emissions. Depending on how much we can get, we can go pretty far down. But it also increases the costs into an industry that can barely keep its head above water. And so while one's moving in the right direction, the other's moving in the wrong direction. You take the blended wing body Z4 and you introduce Jet A, we immediately reduce emissions because we're burning less fuel. And because we're burning less fuel, we're reducing cost. Moving both in the right direction, all from an airframe. Now we introduce SAF, and because we use less energy, we can go further on that limited resource. SAF will have more impact in a more efficient aircraft. And even if the costs go up, we've actually produced some headroom to actually absorb some of that cost. Now, part of the learning curve is also in experience, and part of the value we need to deliver for airlines and for passengers is absolutely around experience. So this might be the most technical slide we'll have today. I think we've all seen this ticket before. If you're an expert at seating charts like me, you'll know that you'll notice a few things here. I'm in row 35, back of the bus. Seat E, I'm in the middle. Probably next to a lavatory. This isn't going to be a great flight. I've got to board almost an hour before the flight, 7:25. Man, I got to set my alarm for 5 in the morning to get to the airport on time. And I'm in group 9. There's no way there's going to be a place for my bag. And other than telegraphing that message, isn't it not the best position in the world for an airline to say to a customer, there's 8 groups more important than you are? So we're working on a cabin today that hits these real human aspects, that addresses the anxiety we feel before we board, that gets rid of things like group 9. This cabin space is no passengers more than 12 rows from the front. We have fewer middle seats and some configurations with no middle seats. Every person has a place for their bag, dedicated, with your seat number on your bin. It'll accept, it provides accessibility for handicap and reduced mobility folks with direct access to any cabin, and reduced handicap lavatories throughout the aircraft. And these are just the beginning pieces. This is our product, and we're working on solving these and many more issues, and also developing a more comfortable space for the passengers and crew. Now, the other part of the learning curve is maybe a little bit less obvious. The path to zero, of course, is tied to emissions. But to have impact on that path, you need to do things at scale, and you need to deliver a product that people want to fly. And so one of the most interesting things about the blended wing body aircraft is because the shape is different, we can actually size it to go exactly into the middle of the market, where the largest demand is, and yet there's no supply. So these are normalized passenger counts for 3-class configurations, but you see a high demand for around a 200-passenger aircraft. This is in the larger 737, A320 family. And then we have no supply in here. This is not a natural curve, right? This curve would want to fill itself in here. The remarkable thing about the blended wing body is that mid-market gap between the wide bodies and single aisles. We can size the aircraft right into that middle space and do it efficiently, which has always been the challenge. It delivers the capacity the airlines are looking for and does it with the range to address up to 90% of the market if we looked at it by revenue passenger miles or kilometers. But if you're going to do that, if you aspire to run a series of missions through multiple aircraft types, you need to be more efficient and you need to be more comfortable in the future. 40 to 50% more efficient than the wide bodies out there today and more comfortable. And in the coming months, hopefully some of you will have a chance to get in the cabin and understand that. And even against the single aisles, 25 to 45% more efficient. And critically for this, as we fly further, and the longer flights on the single aisles, we know, it's one thing to go from here to Hamburg on a flight, for instance, but it's another thing to be on a single aisle for 6+ hours or maybe even longer. The ability to have that comfort as we fly out at much longer wide body ranges. So in many ways, this is an aircraft that actually sees the market as it exists. In the payload range curves and any market forecast you typically see, we hear big planes fly far and small planes fly short. And it's really hard to get into that space in between, which we fit right into. But the multi-mission capability of being able to fly both those missions means we see the market as it is. Millions of people buying millions of tickets a day to thousands of destinations, not by the product that supplies, but actually by the demand of the market. And so we're designing our aircraft to best serve the market demand. It's a transcontinental size aircraft that can do short haul and long haul better than any aircraft today if we're looking at both efficiency and comfort. And as such, can satisfy a large amount of the air traffic out there. And so why is this critical? It does a couple things. It means airlines could have simpler fleets, but it also means as we move toward the march on climate, that this is an aircraft that actually moves the needle. This is an aircraft by itself that can make a difference. So what might that look like? We've seen a bunch of these charts in the last couple of days. This one is a little bit lighter, I would say, on when we add up the fleet renewal and the operational improvements. Then we see heavy reliance on SAF and other. And why is this a little bit dangerous? Well, we talked about SAF and the potential price increases, but others often just too vague. And vague things tend not to happen. We'd like to take a little bit more control of our future. So in this example, the revolutionary aircraft may be a little bit more accurate, but they're also too little too late to actually make a difference and to eat into the vague and the application of SAF. But this chart forgot about Jet Zero. The blended wing body will accelerate the revolutionary replacement starting in the early 2030s, right? 2030 when we come into service. But it also magnifies the impact of SAF. And the combination of those elements alone, we drop the environmental impact considerably. And remarkably with this aircraft, the shape is actually perfect for the application of hydrogen. And because it uses less energy, it makes hydrogen easier to accomplish. And it delivers hydrogen at scale. A hydrogen version of this aircraft will be 160 to 200 passengers with over 3,000 nautical miles range. A plane that could fly multiple segments and come back to the place that actually refuels with hydrogen, so you don't need hydrogen at every airport. And now we're talking about a very small percentage, and this is notional, don't take me literally on this because there's 1,000 ways this could go, but the impact of an airframe could actually make a big difference. From my side, as working with the product team, it's a remarkable thing. We've been given this amazing new technology by Mark and our engineers, and our job is to simply extract the most value from this technology. How do we position this aircraft to deliver the most value for the most stakeholders? And I've worked on a lot of projects through my career at Safran and in my own design consultancy, working on new mobility projects. This was the only one of the new mobility projects. I had a chance to work on supersonic, eVTOLs, some new business jets. Fantastic technologies. I'm rooting for every one of them. But when we saw this one, this was the one we said the world needs. And so I rolled up my design company into Mark's company, and with pleasure, I'm here today. And so value for stakeholders is really a remarkable thing in the airline industry. It touches so many people. This is the first product I've ever seen that can move the needle forward for everyone it touches. And that's a remarkable thing about being on a new learning curve. If you're a passenger who wants a space for their bag and a little bit wider seat, you don't want to sit in a 17-inch seat on a 10-hour flight in the back of the bus. If you're a crew member who just wants the job to be the way it used to be, I don't want to be a policeman and tell people what to do and move bags and handle all that. I want to help, and I want to be the ambassador for my airline. If you're an airline that wants to make money and drive toward your 2050 targets, and quite frankly, just deliver a better product to your customers. In the airports and communities we serve, airports where we can turn at the gates quicker and potentially up the throughput of the limited resources we have, we have at airports, and the communities we fly over with a lower noise profile and less emissions. And then I think lastly for our industry, when we get on this new learning curve, our belief is Jet Zero is good for the entire industry. BWB is great for the entire industry, because when we deliver this aircraft, we'll compel others to follow, and the entire industry will be propelled forward. Thank you very much.
All right, Scott, appreciate you leaving time for discussion. You know, one of the missions of the organization here is to stimulate discussion amongst our community. So I think you've planted a few seeds here, Mark as well. And before Mark comes back up, I want to take 10 minutes to hear some questions and discussion points from the audience and have you and Mark interact. So let's open it up. In the back? All the way in the back, and I'll come back to you, sir, right here in the middle.
Michael Newberry, AIRLINER. I'm wondering how the usable lift compares with CL Max.
Could you repeat your question, please?
Yeah, Michael Newberry from Saab Aeronautics. I'm wondering how the usable lift compares with CL Max. And I'm thinking lateral directional stability and the pitching moment curve. Your control, are you using split flaps, for example?
Scott or Mark?
Yeah, so the, really, so you're wondering how we can exploit that center body as part of it, and how we can control it, which is an earlier question, and trim it. The airplane, the blended wing, fundamentally all it is taking two things that were separate and making them one. And we just kept doing that and marched everywhere until we were getting it down to as flat a thing and as integrated a thing as possible. But there are a couple surprises on the flight controls and stability control of blended wing aircraft. So we're doing something fairly similar to what Boeing has done, or the B-2 bomber. We have multi-input, multi-output controls. The center body has a bank of about 6 independent elevators. They all look the same, but they're split. And we have, right in the pinchy part of the wing, we have what we're calling a flap, and it has, I think it has 5 panels. And outboard, we're calling it an aileron, but it's an elevon rudder vader, whatever you want to call it. And we have the winglet rudder. So the winglet rudder does its one job. I do yaw damping, I do turn coordination, and I help out with an engine out. Most of the engine out benefits come from the control system on the airplane not doing what we did in the past with B2, outboard aileron, it becomes a drag rudder. We're using those multiple surfaces and we're doing this called crow rudder. Much more linear, much quieter drag. In terms of the trimmed CL Max, the way we're getting it is we are working on that setback from the angle at which we don't want to go deep into. So the alpha limiting system is very much like on most T-tail biz jets. And so, you know, it accounts for the rate at which you're increasing alpha and so forth. Our trimmed CL Max, if you were to base it on the total area of the airplane, the total platform is like 1.0. If you put a trapezoidal wing underneath it, and one we're used to, it's approaching 2.0. So that's trimmed at forward CG. And all of that depends on the way the airplane behaves to develop those CG limits that are required, CG range that we're required to cover, and then the aero limits that will do it. There's quite a few fun surprises in what happens.
Did we answer your question?
Yeah, very good. Thank you.
Okay. Can you pass the mic to the young lady in front of you?
Hi, my name is Dahlia Pham. I'm from NASA Ames Research Center. I did have a question. So I was wondering if there will be kind of based off of this, a consideration for kind of having a twin tail in the back or maybe like inclined twin tails, because I was thinking that, you know, as I was watching the evolution of the different like wing bodies, I noticed that there is a continual sweep. So it has me wondering, is there enough, you know, surface area for the control surfaces? And also that the winglets that are kind of shown in the graphics, those I can tell are the aerodynamic winglets. So I was wondering, because, you know, you did mention there's going to be a split rudder flap at the wingtip, and for the demonstrator, correct me if I'm wrong, that's going to be kind of sized to a 767, right? And so I was wondering if that split rudder flap gets pretty heavy at the wingtip. Sorry, I was talking to Alon Crow about it. So.
Right. So yes, for engine out, we use the winglet rudders, and that's small, right?
Right.
What you saw up there is small. But they're pretty effective. But the big muscle we get from crow rudder, so it's like a drag rudder. And if I want the airplane to yaw right against an engine that's hot over here and dead over here, the right wing will have the elevons doing this. The way that we're able to get minimum air control speed equilibrium and the pitch acceleration we want in a go-around on landing and the pitch rate at liftoff, all these different things has to do with two things. One is our landing gear that basically relieves all the burden. The flight controls don't have to do anything for rotation. They're not sized by rotation or takeoff at all.
Oh, how so? Could you explain the?
Yes, so that's our landing gear innovation called the pivot gear. Now we call it takeoff gear. But in any case, then we're not asking aerodynamics alone to rotate the airplane. And there are two reasons why. One is that we may not have room to put the landing gear where we want to. The other one is that well, I'll stay with that. That's the first key thing. But we're revisiting all of these every time we cycle again. We're going back, we did analysis of alternatives several times now over the years, but we keep redoing them as some of the rules change or as we learn more. So the tails on the X-48C, I think they were first proposed by our old propulsion buddy.
Ron Kawai.
Ron Kawai, a retired fellow who's brilliant and helping us with this stuff. And he wanted to locate some acoustic shields at the nozzle exit. And then they started looking at them as control surfaces and said, hey, we could do some stuff. The main thing that they found was that I can use tails on the body, fewer aeroelastic losses, fewer flutter considerations, and then free up the main wing to incorporate shared wingtip technology. That's the interesting thing. With the winglet, it's a different thing. Yes, we get gains. Yes, we get a twofer. I don't need a separate tail. So right now we don't have a tail on the airplane, but that could change.
And will the winglet design also evolve too?
Oh,
based
absolutely.
off of some of this?
And on all of our product designs right now, we do have bigger winglets than you saw there.
Okay,
Mhm.
that makes sense.
Yeah.
I'm sorry to ask one more question about the winglet. So, you know, the split drag rudders, was that also on the X48B by any chance?
The X48B and C both used
have
the B2 style, used commonly, you know, aileron can split and be drag also. So they both did that. And the C model, which had the tails as well and no winglets, they still had to use a little over half of the yaw control for engine out was still coming from the split rudders, split aileron rudders.
Yeah, I'll hand over the mic, but just one curious question about the engine mounting or the center line. Does that mean that the OEI yawing moment, is that less than it would be for tube and wing with the wing-mounted engine?
So
Or approximately so?
it is somewhat less.
Okay.
And when we look at the fratricide question, the 1 in 10 rule for the fan, the 1 in 20 rule for the turbines, we end up, you know, with a spread like 11 feet off center line, so 22 feet between engine center lines. Does everything we need there. And we have the blessing of being able to rig the engines so that no uncontained engine failure could pop the pressure vessel or hit fuel. So the only thing it'll hit is dry bays.
One last question.
Thank you. Roland Gerhardt from Germany, from the DG Lab. I have a question concerning the thrust requirement for the engines. What kind of engine do you want to put on there? Because you want to keep the technology as is, as it is available right now, but in the engine area there, the GTF is a little bit smaller probably for a 250-seater. What is your requirement, and do you anticipating any new engine technologies needed for your fuel consumption expectations?
So this is kind of surprising, but we'd all love new engines. But the answer is no, we can use existing engines. But it's interesting to consider what happens when you have an engine that clearly has the greatest level of technological advancement, things like geared turbofan, things like LEAP, very high, doubled the bypass ratio from their prior engines. But when your airplane gets real efficient, the engine isn't getting stressed to do all the lifting. And so I'll just leave it like that. You get a very interesting, surprising answer.
This is a very thoughtful comment about the airframe being so efficient that we don't have to put the stress on the engine anymore. That's a game changer by itself. And I think people really need to think about the optimization that has gone on with tube and wings and high bypass ratio engine technology, and how that does not apply to the blended wing body. So that's food for thought. So in the meantime, I'm going to go ahead and transition because we're at the half-hour mark. And I think Mark's coming back up. And hold your questions. There may be time. I might be able to get to you next time. Right? So let's turn it over to Mark and give him his 30-minute slot here to conclude the Jet Zero discussion. And remember, after Mark's 30 minutes is over, we're going to have Dr. Jimmy Ty from Georgia Tech, and he's going to kind of give us an independent assessment of some of these performance gains that we're after. So really good presentation coming up from Jimmy, so I encourage you to hang on for that one. So in the meantime, over to Mark again.
Hey, thanks, Faye. So I want to tell you a little bit about the demonstration activities that are going to lead to our big demonstrator. cool. We got past the cool part. So the landing gear system, novel landing gear system, worked beautifully with very, very small control surfaces. And our test program is well underway. Philosophically, I think you've heard this stated differently many times: build, test, break, so on. We're doing the same: build again, test again, but then validate. So got to make those first ones faster. And so to do that, our Pathfinder program is actually not one airplane leading to the demonstrator. It's several airplanes that are going to lead to the demonstrator. We've been flying in the foreground. There's an airplane we lovingly call Foamy, because we told our team members who built it for us to say, hey, use boogie board foam and cover it with monocoat. Do not make fancy molds and stuff. We just want to go out and want to bash around and crash around and pop the wings off if we need to, which we did. That airplane has been immensely informative. Still has very small control surfaces, and it has the takeoff gear implemented, which is why you could have such small surfaces. The one behind it is the 12.5% scale program. That's where we're putting everything in that we're going to do before we go all the way up to the demonstrator. The demonstrator needs to really have a bunch of risk burn down on our landing gear concept, because we're relying on it. And there's some interesting benefits from that landing gear that I'll touch on a little, but in the process of doing all these things, we get to do all the stuff that we have to do at the end. Test planning, learn how to run the team, learn how to dispatch the team, getting all of our checklists together, all those things. It's been a great process. So on the left, we have our little Foamy 4%. We're building right now 3 6.25% airplanes. The first one's going to fly shortly. And we're calling those the SV for scale vehicles. And then the 12.5% scale, AV1 and AV2. AV2 is out of the molds now too. So we're going to be able to be testing the 6% scale and the second airplane of the 12% scale almost at the same time. We just won't work so hard on the second one while we do some work that is more fun, touching the boundaries, going beyond the boundaries, doing limiter assaults on the alpha limiter to understand how much setback we need in absolute alpha or in alpha rate and so forth. But the airplanes on the right have fully functional, dynamically scaled landing gear suspension. So the spring rates, the compression damping and rebound damping, the tire squish rate emulate a full-scale airplane. They're fully retractable gear as well. They're a little overbuilt because when we were doing one of the design reviews, Professor Elon Crow challenged us on some of the load cases we analyzed because we kind of scaled the gust for landing, the sink rate at landing, and the gust that would produce it. And Dr. Crow said, I don't think the wind has been notified of this change. I think it's going to do just the same as it would on a Part 23 or Part 25 airplane. So the landing gear are way overbuilt structurally. So in reality, they'd be much more lacy than what you saw in some of those images. So we did So we did lots of work with the Foamy. This is being chased by a high-speed camera drone. And naturally, there's takeoff and landing, but we did a bunch of air work. And remarkably, in that little airplane, we had a Spanish autopilot that we're really excited about for the unmanned aircraft and developmental world. It's called Invention from Spain. It was the only, none of the DoD provided autopilots like Athena's and so forth could support what we had to do. We have lots of control surfaces. They're all small. In fact, on the real airplane, we only need 2 actuator types for all the flight control systems. We're getting it down to 1, 2, just adjust things a bit. That's pretty cool. But you got to talk to all of them, because sometimes they're doing this and sometimes they're doing this. And that means you have that many more channels of control that you need out of that flight control system. So we fly this pilot on the autopilot, and we can fly it totally autonomously as well, do pre-canned maneuvers, pitch pulses, roll pulses, get the damping, subsidence on short period and Dutch roll, as well as the other basic stuff like stat long stab and steady heading side slips. That's the beast. And set out to do from day one was essentially replicate what you would do to certify a real airplane. So some of you might not appreciate that takeoff field length, the critical takeoff field length is never flown. You don't actually fly a takeoff to figure out what your critical takeoff field length is. It actually is almost irrelevant because you can do all kinds of stuff. It's when you put the V1 limits in. Engine failure, you have to have a minimum ground control speed that's less than or equal to V1. For decision speed, you want to make sure that if I'm still going, I have an engine failure, I got enough control on the ground to maintain track and heading on the runway. And you have all the other relationships, like V liftoff has to be so far from minimum unstick speed. Minimum unstick speed, you guys have seen, you set the airplane on its tail skid, it makes a bunch of sparks, and they slowly let it fly off. That tells you when the airplane can just fly off. That's the slowest speed at which the airplane can make lift equal weight. So the rotation speeds have to be declared lower than that, faster than that, so that when I pull up on the stick, the airplane is going to be separating from the runway faster than the back end is going to descend. I guarantee I never whack the tail. So we're going to do all those maneuvers. We'll assemble them just like we would in an FAA thing into a takeoff field length that's determined mathematically by all the constraints. And we'll do exactly the same thing. We have to fly VMCG, V2, we got VMU, VRMIN, all those things. And landing similar things. So this is a lot of airplane. It actually has an N number because it's over 55 pounds. So we work with the FAA on when and where to fly it, how we're going to use it, and the emergency backups we have. The airplane has a ballistic parachute, actually just like X-48. And we have 4 airbags that deploy also, so that if we have to pop that chute, when it lands, we haven't bent anything. We haven't popped a landing gear because we've got these airbags. And they're really cool how those things work. Do you guys know how airbags work? On an aircraft? They have a teeny tiny fan, super lightweight shape that's going to be the thing you want. A rectangle or a circle that's going to be under the airplane and take the shock. It's sort of like making an airbag out of a t-shirt. So the neck closed, so the bottom closed. And you're going to put, in the neck you're going to put a fan. You're going to sew the bottom closed. And you're going to put rubber bands around the sleeves. Hold that closed. So a little tiny fan, very tiny delta P, fills it up easy. Very lightweight, but with very light pressure. Then, when you hit the ground, there's a check valve where the fan was, and then it just pops those rubber bands off, and dumb as bricks, and you've set the diameter of the sleeves so that it exhales just the way you want to get rid of that energy beautifully. Those things are fabulous. It's all dynamically scaled. I think many of you are familiar with that, but just like we do scaling laws in aerodynamics, you could do the same thing in kinematics. And I use overuse the example of in the early days when they were doing the first movies and discovered that filming a model train on a set looks like a model train. But if instead you slow it down by the square root of the scale factor, or speed up the film going through the camera times that factor, then you can get something that looks very natural. Even waves on water, splashing, dust kick-up, all looks natural when you do that time conversion. That's what we're doing here. So the Pathfinder program has had an immense amount of ground testing. So landing gear, which you see has some mechanisms in it. And we did strength tests, dropping it from a drop height of like 3.5 feet. That hurts. But we also did a bunch of cornering load testing, brake balancing. We did a lot of work on the link up between the mains and the forward gear so that you get the apparent pivot point being very near the CG. That's why we can rotate with tiny control surfaces. And sometimes take a look at X-48. Great airplane, but look at the flight control surfaces, especially on the bottom. They're about 5 times bigger than ours in chord, because that's what it takes to rotate the airplane. if you don't have help. And what we found was, you know what? Let's let the landing gear help. Because we already have piston-like things we can push on, so why don't we see what we could do? And that's what we've been developing. I had a lot of fun driving it outside. It was cool at Long Beach Airport. We rolled it out and had to drive it around. And there are people at Long Beach Airport who just spy all day long. And when they see something interesting, an airliner with an engine on fire, whatever, and they put it on the web. So the day we put that out, it was like a half hour later, it was on the web that we were flying this crazy airplane, or taxiing this crazy airplane. As I said, it's experimental, so we have to, in some circumstances, we'd have to fly with the chase plane, not always, much like Predator would in its checkout flights. We did a very extensive high-speed taxi program, and the reason is that our flight control system and the landing gear are working together to affect a rotation. So we wanted to see how it behaved with an abused rotation at VR -5, VR -10. We wanted to see how it did with an oversped rotation, and we had to be very careful because we didn't want to fly. We were there, right there on taxiways that Long Beach Airport let us use for test. And so there was a NOTAM to tell people to stay away from us. So this is some of that test. You can see the elevators moving there. Oh, come on, you could do it. See the pilot, he was trying to see where it was going to go. Okay, there it goes. You can see the nose is just moving a little bit. It's slowed down. The reason it's just moving a little bit is because we just wanted to make sure that the light went out, saying that we were in compressed mode, that the pivot gear was working. We didn't have to continue and take off. That was fine. So we had a ton of testing, only looking at that incipient part of rotation. Dynamically scaled beast like X-48. And we actually tested it at a place called Crow's Landing, which apparently NASA owns and gave us permission for. Mainly, it's used for cattle to graze between the runways. And our 6 1/4 airplanes, this is the buck assembled for the molds. So the airplanes are all out, the first airplane's already out of the molds, being assembled now. And what are we going to do with this airplane? Well, Foamy was an airplane we could crash and smash and bash, but it was a microscopic Reynolds number. This airplane on the 12% scale airplane are at Reynolds number you can work with. And something I haven't mentioned, but that I don't hear of very often. So we created a new airfoil stack for this airplane to represent full scale. At first it might sound like cheating, but what we actually did was we took CFD of the full scale airplane at full scale Reynolds number, going through a pitch sweep. We found the critical stall stations, looked at what the CL max was, the alpha critical, so on and so forth. Then we substituted those with low Reynolds number airfoils that had the exact same alpha stall and CL max, had the exact same CM delta E, CL delta E, up to the real deflections. We had to use really fat trailing edge airfoils to get it done, but we nailed it. We absolutely nailed it. So we had the exact same alpha zero lift, CL alpha, CL max, alpha stall, and max and min pitching moment on those controls. But the airfoils don't look like transonic airfoils. Just lots of fun getting all the pieces done. The full-scale demonstrator is the real objective, of course. We're going to do a ton with that. The very first thing we have to demonstrate is a 30% improvement above the current mid-market airplanes. They're a little older airplanes, right? We don't have really any new mid-market airplanes. But some of them have remarkable LOVs, more than airplanes flying today. So we're going to start out by just doing basic flat envelope expansion. We're going to take the airplane to VFC, MFC. That's flight control speed. We also have an amazing amount of commonality with where we think the product's going to be, because we have an off-the-shelf philosophy. It's COTS, COTS, COTS. We don't need any special technology to enable the airplane except the extensible nose gear. And engine airframe distortion, we're going to demonstrate. Again, it's really surprising. If you do all the analysis, you don't ever see a problem. And that's, again, when the airplane's making that much lift, it turns the flow right to the engine. So it never sees angle of attack changes ever. It only sees side slip changes. And so the side lips of the nacelle are fat with big radius, and the upper and lower lips can be very sharp. We're going to refine control laws, of course, and we're going to achieve level 1 handling qualities and no worse than level 2 after significant failures. And we're going to have a robust envelope protection system in alpha, beta, bank, and load factor. And we're going to test this takeoff gear in a bunch of adverse conditions. So the gear raises the nose, so it gets longer by 4 or 5 feet. And that means the loads turn into bigger moments, right? And so you got more stuff in there. And you might first think, why the heck are you making that thing? Doesn't that go against the thesis of making it simple? The airplane is pretty remarkable. We didn't talk about this, but we don't need slats. No slats on this one. We don't have high extension flaps, nor did the X-48, but we don't have it either. But we don't have spoilers, no spoilers. We don't need them, because we can do this with my ailerons, elevators, and flaps. Get all the drag I want. Very quiet and much more linear drag than even a spoiler does, let alone a split panel. So the airplane is crazy simple. And then we have all these very similar panels with a common actuator. So it's really amazing in that case. The reason that you do it and it pays for itself is the heroics you have to go through to get enough pitch control power, to the question earlier, for takeoff rotation. Once you're airborne, you got all the pitch control power you'd ever need. It's really takeoff rotation that has designed the blended wings who have gone far enough into the design to really make sure they can do all the cases, including abused takeoffs and so forth. So when we do that, now we move that job to the nose gear. That means we can have an uninterrupted cabin in our airplane. We can find a place where we can park the landing gear that no one else is using. And so that's huge. That's a huge thing. And the other thing came as a surprise. You probably noticed that the wheels are kind of far back on the main gear. In essence, we're trying to pop a wheelie with a grocery cart instead of a lawnmower. A lawnmower is easy, right? It's got a long tail arm. Shopping cart does not. So how do we rotate this thing? Well, we don't ask it to rotate about the main gear in that aft position. We ask it to rotate very close to the CG, forward and up, by having a teeter-totter feature that allows, it's not a teeter-totter, but it's a mechanical analog that allows us to pitch, fly the airplane off the ground. The ground reactions are not affecting pitch in any way on the ground until you derotate and you hit lock. Okay, so that system means I have 3 gear, 1, 2, 3, that actually have almost the same load. So the nose gear is the same as the main gear. Same truck, only difference is it has steering. Race cars and automobiles, when you hit the brakes, you can steer. There's no special magic there. So that's not an issue at all. But the interesting thing is when you harvest the weight transfer of the airplane on the brakes. So I hit the brakes, right? Down beneath me, something's pulling aft. My inertia is keeping me going forward. I pitch down, the load transfers from the mains to the front, right? The more I decelerate, the more of my load transfers to the front. We throw that away today. We have rolling gear in the nose gear. We don't keep any of it. With brakes on the nose gear, we get a 30% increase in deceleration with the same carbon brakes, same rubber, and same asphalt. It just falls out. So that takeoff field length benefit also de-stresses the engine. So the benefits of that really cascaded, and that's why we're pursuing it. We're making it simpler every 6 months. And the other thing we want to do with the demonstrator, I probably buried the real punchline. This demonstrator is going to be flying 2 years before our T1 production article. And if you think about it, you say, wait a minute, that doesn't sound like good planning, because that's not enough time to do that and then do. So we're doing them somewhat in parallel, because the Aero OML, the basic CGs are well understood already, and we can predict them very well. So we're going to take that airplane. T1's going to have the real stuff. It'll be a little bit different on the Pathfinder, but the Pathfinder allows us to go do all the air work, takeoff and landing, all kinds of stuff to reduce the the amount of development testing that T1 will have to do. We're going to be learning from flight test data 2 years before the big guy. The reason we can run them in parallel is the structure does not match the real airplane. We're allowing it to be dumb. That's okay, you can be dumb, because who wants to break an airplane structure in the air? No, you do that on the ground, which is what we're going to do. But the fact that we can get this developmental stuff done that early is amazing. Thank you very much.
Okay, thank you all for hanging in there so far. We've got one last presentation, but before we get to that, we've got 7 minutes for the Jet Zero team. Yes, the young lady on the back row, and then I need to get back to this gentleman in the 4th row here that raised his hand. Okay, go ahead.
So the question relates to, wait a minute, if I need this gear to take off, then its failure suddenly is on my problem list, right? I have to have redundancy. Well, how do I get redundancy? Do I put 2 nose gear on? Actually, you could. Turns out it works really well, but that's not what we're going to do. It turns out that if you take a bit of a preset, when you're at brake release, maybe you go couple 3 degrees towards your rotation. Just enough so that if you had to do a takeoff and that thing jammed, you could complete the takeoff and you use up the 15% margin for all engine takeoff field lengths. So the field length gets scheduled for any airliner that you certify is the more critical of the balanced field length and the all engine continued climb takeoff field length plus 15%. So what we're doing is we're not saying that the engines fail and suddenly the nose gear at that moment jams. We're saying that actually there's virtually no likelihood that those two will happen at the same time. And so what will happen is that when we're taking off, and if that nose gear were to stay put and did not respond to commands or didn't move any further, then our runway length is increased for takeoff, but it's still within the 15% pad for scheduled takeoff. Does that make sense? So that's how we're doing it, because you have to do something.
Okay, thank you. I want to get to your question unless it's been answered.
Matthias Meusen, Airbus Commercial Future Projects. I have a question on the previous presentation where you showed the lasagna pie chart from 2030 on really taking an impressive uptake. This for sure has some assumptions about the production rate, about the number of aircraft that needs to come into the market to achieve that. 2 questions of that. What has been your assumptions? And did you use Cascade to do some of the calculations?
Sure, thank you. Yes, that was a highly notional chart, but I think that the intent to show there is, as Jet Zero comes to market with an aircraft that has the benefits that are highly valuable to the airlines, fuel burn, added to a better experience, and multi-mission capability, we believe the uptake of the aircraft will be very quick. Our ambition is pretty simple. It is to build such a fantastic aircraft that our challenge is not how many can we sell, it's how many can we build. And so our plan is pretty straightforward. It's in 2030 we start ramp up to 20 aircraft a month in our first facility as we get to the middle of the decade, and then demand willing, we copy and paste that facility several times. But I think that's only a small part of the story. This aircraft, when it flies, it'll put an airline into such an advantageous position. You could drop it into any route or market and instantly dominate in that market, that the existence of a BWB in the commercial market will compel others to follow. If it's not a BWB, it has to be a like product. And so our belief is the entire industry moves forward, and the act of Jet Zero existing actually becomes beneficial for the whole industry to catalyze everyone to make big moves forward, so we can see those kind of numbers.
I take that as an invitation. Thank you.
Or a challenge.
Right.
Let's see, Fossey Kafeki in the back there.
Yes, good morning, Fassi Gafiek et Bombardier. Nice project. I just, maybe I didn't see it, but I want to ask you, what's the design cruise Mach number?
Design cruise Mach
Oh,
number.
so, yes. So the design cruise Mach number is 80.
Yes.
And you're probably aware that blended wings have a natural Sears hack cross-sectional area distribution. If you look at the cross-sectional area marching nose to tail on a tube and wing, it goes up a little bit, there's a tube, and then it hits on a cell, and then there's a big lump of spike where the wing, then it goes back, and it comes back. Blended wing is very smooth. It looks sort of like a sheared aft Sears
So
hack
what is
distribution.
the sweep of your wing?
The wing's about 30 degrees.
30?
30.
30 degrees.
So because of that Sears hack benefit, giving it the capability to go to 8.5 Mach and fly there and use that as your MC is right there for us. It's totally fine. You have no compressibility issues. In part because, of course, you're going at lower CL and you're going faster, so they're just fine. We also have been, in our design optimizations, we also take a look at lowering Mach number, because people are looking at that, and you can save some fuel doing that. So when we do the optimizations, I mean, you can imagine there's all kinds of terms that we have and cases we look at, but we look at a couple Machs below 8.0. We do a lot of stuff at 8.0, and then we look at between 8.3 and 8.5 on the fast end as a cruise condition. So the optimization of the airplane is informed by all that.
Yes. I was just asking these questions because you have an airplane without a slat.
Yes, that's right.
So it depends what you have as a sweep angle, because otherwise you have to contend with a lot of. And you found that that was good for also field length?
Yes, absolutely. So with a 30% improvement in braking, you get that part.
Okay.
But the other thing is, this is really geeky, but CL VMU, lift coefficient at minimum on-stick speed, blended wings are completely designed around that. That is the entire thing. Because if you don't have a pivot gear or something like that, takeoff gear, then the control surfaces have to be huge to get the nose up, and guess what that does? That dumps that much lift. So just before, the X-48 happened just after I left, or started just after I left Boeing. But before then, what we were looking at was that the actual liftoff condition, I'd given up half of my lift just to put the nose up. So in fact, you got there, you only realized like a small fraction of what you think you would get at that deck angle. So getting rid of that burden on the flight controls was huge on performance, especially takeoff performance. So we're seeing typically, I mean, it sounds crazy, but sometimes we see 40% reduction compared to a tube and wing. Mostly we see 25, 35%. On landing field length, we also get 25% benefit because of the braking benefit. There's no other magic there. But remember too, Bombardier bizjets, Gulfstream bizjets. Bombardier has slats, high extension flaps with the carrots underneath, right, to fit all that equipment. The guys at Gulfstream did it different. They have no slats. They hid everything inside, and the flaps are not as powerful as before. They build the airplane around the flying high thesis. If I'm flying high, that airplane's going to need a wing for cruise that's bigger. And then when I back up the flight profile, shoot, I got plenty of wing for takeoff and landing. It's not at first obvious because it seems antithetical that you would say that adding wing area improves performance. But with the whole ecosystem, it absolutely does.
Thank you.
I'm going to have to cut it off there and apologize for the folks that had a pending question. Jimmy Ty flew a long ways to get here today, so I want to give him his 30 minutes. But before we do that, I want to thank Scott and Mark for their 90 minutes that they gave us. Wally's going to introduce Jimmy.
Yeah, thank you, Faye. Yeah, Faye has to leave for a meeting now, but I just want to introduce Jimmy before he starts his presentation. I'm Wally Rishamolu from Pratt & Whitney, so it's a pleasure to be here. I'd like to introduce Jimmy Tai, who I've known for several years. Dr. Jimmy Tai is currently the Associate Director of the Aerospace Systems Design Lab at Georgia Tech. And he also holds the position of Division Chief for the Advanced Configurations Division of that same ASDL. He has conducted a lot of research, and he's still conducting a lot of research and development in the area of propulsion system design, the area of multidisciplinary analysis and the applications, and also looking at advanced approaches for technology assessment. So it's a pleasure to welcome him here. And as you heard from Faye, he's providing an independent assessment, an activity that he has done with the US government, NASA, DOD, and FAA, and he's also doing for this particular study. Thank you, Jimmy. Yeah.
Thank you, Wally. Excellent introduction. I stand between you and lunch, so thank you very much for sticking around. There's plenty of seats in the front for those in the back who want to come in. I want to make this as informal as possible. Again, thank you very much for the introduction. Faye, thank you very much for this opportunity to present. Again, I want to look at a performance comparison, at least what we hope to be a comparison that's more apples to apples. For those that saw Dr. Jim Heilman's presentation, he did an excellent job about different atmospheric studies in the past. I did the same thing. I saw his slide going, oh, wow, that's great. Hopefully great minds think alike. We kind of review what studies out there have kind of quoted the performance difference between a tube and wing and a BWB. And we felt like there was a little bit of apples and oranges, maybe a tangerine and orange comparison versus an apples-to-apples comparison. So what we want to do in this study is basically size the tube and wing and the BWB for the same requirements, compared against and optimize both vehicles in similar fashion, similar capabilities, and also size of a similar technology level. And then, of course, the same engine, but we're going to break that rule in a second, as you'll see. So again, this chart just shows you that there's many different studies that show different numbers, and we're going to add to that literature. So again, like I said, we want to look at just the configurational change benefit going from a tube and wing to BWB. Again, try to do a more apples-to-apples comparison, isolating the airframe impact on the performance. Both are going to need identical engines. We're going to design for the same payload, same range, and fly similar missions. And both configurations needs to be designed and analyzed the same methodology and disciplinary fidelity levels. So what we did was build a parametric CAD model for both BWB and the tube and wing for the same passenger count, optimize both geometries using CFD. I'll give a little bit of detail about how we optimized and what we optimized. And also use CFD base to generate the entire drag polar for the mission. Develop a common engine model for both vehicles, both configurations, and then conduct a mission analysis for the same payload range. We did a lot more than these comparisons, which I'll get into a little bit, but the first comparison is going to be using identical engine, but there's two variants for the tube and wing, one for metal wing and another one for composite structure. The second set, second set is actually optimize and resize the engine for both vehicles to see what's best for each one. Again, the tube and wing has two variants, a metal and a composite variant. And then finally, we're going to compare that BWB against the existing Boeing, notional Boeing 767 family, see how it does. So to kind of get a little bit how we generate the BWB baseline, again, I want to stress that this is a completely independent study. I even though I work with JetZero, there was no proprietary information exchange for this paper. So we usually use public domain data, sketched up the BWB using Engineering Sketchpad, for those that are familiar with ESP, and configure the internal layout for 3-class, 226 passengers. And the overall plan form and internal layouts are loosely based on the public images that JetZero has released. And then the outboard wing stack, again, the starting point for our airfoil stack is based on the SAC 40 published airfoil and twist distribution as well. Again, the baseline twist distribution then will be later adjusted in our optimization. The right-hand side of that slide kind of shows you our starting point for our plan form. I'll cover this a little bit more detail after I do the tube and wing configuration. It's again based on the notional 767-300ER with winglets. Again, we created that geometry in Engineering Sketchpad or ESP. Similar layout using airport planning manuals to kind of guide us on what those 3-class layout will look like. We started the tube and wing using the NASA Common Research Model in terms of airfoil stacks and twist. So that actually will come important. That note will come important when I show the results. Again, baseline distribution will be later adjusted to provide better starting point for optimization or the end result of optimization. The vertical tails are assumed to be the NACA 6400 series. And again, the NASA CRM is providing a horizontal tail and also the airfoil extracted for the near the root. Again, the right-hand side is give you a notion of how we did that. I want to go back. I apologize. Very important thing. Need to recognize my co-authors, Dr. Jay Ahuja and Dr. Christian Perrone, and our graduate research assistant, Reina, did a lot of work. I just get to present it. Not true. I did a lot of work on this one as well on sensor mission analysis. But definitely, and of course, under Dr. Maverick's tutelage. So that was the tube and line baseline. This is, for those who are interested in CFD, it's pretty boilerplate for CFD, so I'm not gonna get too much on it. We did do a convergence study for both configurations. We did use STAR CCM, fully turbulent RANS solutions, steady state. For those that are interested in more dynamic stuff, I don't have any, sorry. The setup, again, unstructured polyhedral grid with a RANS solution. I'm not gonna get into details of how we did that, but I also want to stress that this is, for this presentation, for this invited session, this one actually has a paper, so I encourage you to look at the paper. In fact, there's a lot of details in this slides, but again, it's also in the paper. So the optimization strategy, it's a little bit different. I'm going to just jump to the very bottom left part of your slides. We did not optimize the plan form variables. We have focused on the angle of attack, the twist, at different stations, and also the camber distribution, and then, yeah, pretty much camber distribution, and our objective is to maximize L over D. So we took a slightly different approach, you know, even with those number of variables, number of stations, we're looking at 73 design variables for BWB, approximately 82 design variables for the tube and wing. So what we employed what we call active subspace optimization to kind of reduce the dimensionality. Again, I'm not going to get into details of how we do that. Just a little bit of a explanation in the paper as well. We're able to reduce the dimensionality from 73 to 6 for active variables for the BWB, for the tube and wing from 82 design variables down to 6 as well. And then beyond that, what we do is using adaptive sampling and surrogate models to guide the optimization. So a very critical point on that is we're not optimizing surrogate models. We're using surrogate models to guide the optimization in terms of which step to take in terms of its optimization. We also take a little bit further. Instead of using, so that gives a single point, right? A design Mach 0.8, 35,000 feet is where we're gonna basically optimize the airplane for. Actually, I think that's, I didn't mention that, but it's in the paper of the condition that we optimize it. It might be a little bit higher than that. So we also took the CFD approach to generate the entire drag polar for the flight mission. Again, that's very expensive. So what we end up doing is a sparse high fidelity data for RANS, and then space filled it with our oiler solutions, also CFD. Actually, I take that back. We tried that and didn't work as well as we thought it would, so we ended up with RAND's lower course grid solutions for those lower fidelity ones to kind of guide us which direction to go, looking at like taking derivatives, if you will, and then anchor those points with a more fine RAND solution. So we call that as kind of a multi-fidelity surrogate model for the aerodynamic data set that we need to do the mission profile. And I believe our design point is at 40,000 feet, thinking that I have that plot there. So, and then coming to the engine selection. So what we did for the common engine, we started with a notional PW1133. Thank you, gentlemen, for the person earlier that asked about the gear fan. So we started with the gear fan. However, we revised the core and the fan design and to produce 43,000 pound sea level thrust class in the 2030s. Also, wanted to mention that there's also assumptions that are fairly stated fairly well in the paper of how we get from current technology to 2030 technology. We used, in this engine generation, for the common engine generation, we use a simultaneous multi-design point method. That's well documented. And you see on the bottom left hand there some of the critical design conditions for the notional 1133 that we started with, and then what we ended up with for the 2030 engine, and that's what we'll be using for both vehicles. And then later on, once we say, okay, second comparison, what if we optimize the engine for each of the vehicles, is what you get on the right-hand side. We just give you ranges in terms of what we optimize, the fan pressure ratio at the aero design point, the OPER at the aero design point, our max T4, and also the engine thrust is actually allowed to size for what the aircraft needs. For the system analysis, here's the mission that we're flying for both missions. It's similar requirements. We allow the mission analysis to decide what's the best altitude to cruise at, but definitely cruise at Mach 0.8. The mission is 5,000 nautical miles, carrying 225 passengers. We assume about 250 pounds. That includes baggage for it, and we did do an economic mission as well for 900 nautical miles, the same payload. Every mission has the required 200 nautical mile alternate airport for sizing as well. The bottom right-hand side tells you the assumptions we made for the BWB in terms of the structural weight. And that's actually based on yet another study that Dr. Faye Collier sponsored our group to do back in the ERA days, the Environmental Responsible Aviation Study. So we took that documentation to see how much structural weight reduction for the center body relative to composites, as well as what the weight reduction would be for the outer wing portion and also the aft body portion. Again, we'll document in the paper to kind of set the grounds for the technology for the BWB. So this is the drag comparison. Again, CFD results only, no mission, for a clean BWB and clean tube and wing. Keep in mind that we optimized all those variables we talked about for CFD for that one condition, which is at Mach 0.8, 40,000 feet. No nacelle, no pylon, no interference with extrinsic drag, including these results, and both airframes optimized. The objective is to optimize LOD. And the results show that the BWB, just the airframe itself from CFD results, no mission, peak LOD is about 15% more than a tube and wing. But we didn't stop there. We're going to keep going. But notice that the tube and wing doesn't really did much improvement based on optimization as much as the BWB. Well, we contributed to the fact that CRM was well designed, therefore really couldn't improve on it much further than what we had, what it had. So this is the first comparison for, again, it's a very busy chart, apologize, but again, it's in the paper as well. So you can look at that. I'm going to jump to the next, the takeaway points here. This is the first comparison. Now we add the mission, add the common engine, both flying the same engine, same mission we just talked about, and you'll see the comparison. Look at the operating empty weight. It's somewhere around 16 to 8%, depends on which one you're looking at. Ramp weight reductions, about 10 to 15%. Design fuel burn. It's somewhere around 20 to 24%, depends on whether you're doing metal wing or a composite wing. And then, of course, the Perseus, which is the structural weight assumption that we made for the BWB, and of course, lack of a empennage also helped with the drag part of that. It's also like more fuel efficient and a higher mission ranges, meaning that compared to a 900 nautical mile versus a design range. And also can fly a little bit higher than tube and wing because it's more efficient. So that's our first comparison. Kind of keep an eye on that. Design fuel burns about 20 to 24%. Now we optimize the engine for those 3 or 4 variables we talked about before. It actually performs similarly, and maybe some categories a little bit higher, but not much better. Again, somewhere in terms of fuel burn, it's 21 to 25%, maybe a little bit, ticked up a little tiny bit relative to the metal wing. Now, so that's pretty much CFD based on a notional Boeing 300ER. Dr. Collier says, well, what happens when you compare to the rest of the 767 family? So obviously I couldn't go back and redo all those CFD studies over again. So I cheated. I just compared what the performance is for in the airport planning manuals for the APMs that are published on all the Boeing website to get the performance and the payload range, and basically compared my BWB common engine, 43,000 pound engine, against the performance of what's in the airport planning manual against all the family. So again, didn't do any analysis on the tube and wing side. It's just taking the existing information from the airport planning manual. We're showing that is somewhere, again, picking the same point that's common to all 3 families, the 200 being the most limiting one, and look at that payload range, and flew our BWB and all the rest of the aircraft at the same payload range point. And it shows that for all the vehicle family, we're anywhere from 43 to 52% fuel burn reduction. So that definitely backs up what Jet Zero has been saying in terms of 50% fuel reduction compared to the current middle of the market. So Dr. Collier is a very tough customer. So he says, I really want a CFD study on the 200. So again, couldn't really completely go back and say, okay, what do I do with the current information I have that I can actually kind of morph into a CFD study for the 200. So we decided to take the clean configuration we had for the 300ER, took out the winglets, shortened the fuselage, adjust the position of the empennage, all coming from the 3 view drawings you can get from the airport planning manual. We did just keep the fact that this is a big assumption, right? We took the optimized airfoil stack that we got from the previous optimization for the 300ER and kept that because I didn't have time to finish for this conference, the results for optimizing that again. So, but we did now take that geometry and run an alpha sweep for our RAN solution to generate this cruise drag polar, okay? And that showed is about 21.5% difference relative to the 200 versus the 14.5% that I showed you earlier for the 300ER. Kind of makes sense because it's older aircraft. Hopefully, we'll do better, definitely better than the 300. Then we took one step further. So again, that's just comparing the CFD, cheating CFD, if you will, to the results that for the 200. Then we said, okay, well now we have that. Let's go ahead and fly the different missions. So we took the payload range chart for the 767-200, picked 21 points, and say, okay, can I match the aerodynamics? What K factor or scaling factor you want to put on each of those points for my aero to match the performance on 21 points of the payload range chart? And let's do a distribution. And also fly the BWB for the same 21 points and see where we are. So it becomes a little bit of distribution, not uncertainty, but it's definitely just different points. And we try to minimize the error for each one of my drag scalars, if you will. So that comes out to be anywhere from 36.6% to 35% improvement on cruise LVD. This is not the max LVD, this is the beginning of cruise LVD based on the mission analysis that we did for these 21 different payload range points off design, if you will. So, in conclusion, this is kind of our key contribution. We try to quantify the airframe change benefit going from tube and wing to BWB. Hopefully it's a little bit more apples-to-apples comparison to what's been done in the literature today. With the same 2030 engine for both aircraft, both airframes optimized using CFD. Generated the mission drag pullers for both airplanes using CFD, and then flying both vehicles for the same mission. Extended that comparison to account for engine contribution based on the same engine and different, and also optimized for the right aircraft. And then, of course, compare it to the 676 family. So that showed about 36 to 35% improvement for a start of cruise LOD. So thank you very much for your attention. I guess we're open for questions.
Yeah.
If you have,
So,
oh, actually, that's pretty good. 8 minutes for questions.
6 minutes of questions for Jimmy.
Thanks for your presentation. Just, I was wondering about you didn't mention the ground performance, so the takeoff and landing issue concerning the low CLmax of BWB, and the other issue is if you know Egbert Torenbeck, which you know maybe passed away a few days ago. The second book of Torenbeck was mentioning that for a BWB, the best gain can be achieved at much higher flight altitude, like 50,000. So I don't know if you, because I saw the same 39,000 feet for the both configuration. But for a BWB, he was mentioning in his book that the higher gain can be achieved only if the flight, so also the engine should be.
Yeah, I believe I have to double check the numbers, but pretty sure that the BW flew a higher altitude for our mission analysis. Maybe not so for the same engine one. And we did not do any detailed takeoff and landing for this particular study because I didn't have the time to do the low speed aerodynamic CFD analysis, which is a lot more complex. But stay tuned. That's definitely was our plan for the next step. That's a cop-out, I know, but sorry. Not enough time in the day.
Yeah.
I think we had.
Yes,
Jim.
Hey, Jimmy. Excellent work. But I have to ask you a question that a Boeing engineer asked me about 20 years ago during a non-advocate review when he pointed out to me that there's nothing heavier than reality. Have you actually gone through and done any sensitivity studies on your empty weight in terms of how that would affect your overall fuel burn?
In terms of just kind of jiggering the empty weight factor?
Yeah, you obviously have to make a number of assumptions on the structural weight, the other weight fractions. And obviously JetZero's been doing some great work in thinking through how to bring that down.
Right.
And that's going to have a tremendous impact on your overall fuel burn. So I'm just wondering if you've gone through and done sensitivity studies on that key parameter.
So even though we didn't do, the 21 points I showed is kind of similar because you have different OEW assumptions in that study that I did, the 21 points. Those all have varying OEWs. So that sensitivity there is kind of there, but not a formal one. But yeah, definitely for uncertainty study, we would definitely do that sensitivity on an uncertainty study.
Yeah, I have a kind of, hello? Yeah.
There you are.
Hi, yeah. I have a kind of similar question. I mean, the big unknown with BWBs is that nobody has actually ever built one, so nobody knows how much they will weigh. Well, full scale anyway. So without obviously using spying data from JetZero, shouldn't you be doing an aerostructural optimization in order to be able to say something about the weight of these things?
So for any aerostructural studies, everybody in this room knows, they need a vehicle. So I'm giving them that vehicle, and yes, we are exactly doing that next in terms of taking now, you got a gross weight, you have a planform, you have a twist distribution, you have a volume, you can now lay out the structure. Now we can start optimizing the structure, making sure we actually, the next step, 2 steps maybe from here, is to look at the structural sizing to get to the right jig shape. A lot of people haven't considered that. A lot of the performance here is assuming a particular shape, but whatever you build that shape to get to that 1G flight shape is critical. So in our design analysis, in terms of my division for advanced configurations, also to get down to that static aeroelastic sizing for a 1G flight shape that we can now back out a jig shape.
Okay, thanks.
So,
Good. Yeah. Okay, please state your name and your affiliation before you ask your question. Okay, yes, over here.
Sorry. I think, no.
Oh, sorry.
I'm going to do a very naughty thing now. My name is Joachim Hussen. As I said earlier, I'm from South Africa, out of the bush. And I'm actually very famous. The problem is that absolutely nobody knows that. But I sit here amongst Boeing and Airbus, and we just observed that there was a challenge between ZeroJet and Airbus. And I want to say that this discussion here, which is extremely impressive, and I am totally overwhelmed, confirms the fact that we actually don't know what an aircraft should look like to be most efficient. But it also says the current dominant configuration is not the best. And it is quite a convincing case that you are making here. So it seems as if we are now beyond the question, well, shall we stick to the current dominant configuration or not? The reason why I say this is naughty is because I want to invite you to my presentation tomorrow, same time. Different place, all 3. Where I have bad news for the blended wing body. However, coming from the bush of South Africa, I must admit I can't compete with you guys. So although there might be something better out there, I wish you guys all the luck, and it's a very impressive mark. We actually know each other. I know you might not remember me, but when we tested at Jeff Spedding's wind tunnel, we tested an alternative aircraft configuration, and yeah, so the blended wing, I'd love that we do this work also for another configuration, the work that you've done now, because I believe there is even something better out there than the blended wing body, and Airbus and Boeing.
Thank you.
You must listen.
Okay.
Thank you.
Okay, one more question before we break for lunch. Yes, please.
2 more questions. We'll get Nick in there. Go ahead.
You seem to have produced incontrovertible, irrefutable evidence that blended wing body design is much better, significantly better than TNW. Now, presumably, one of my concerns is, of course, it seems, please correct me if I'm wrong, your analysis is primarily based on steady aerodynamics rather than unsteady aerodynamics. Now, your evidence suggests that blended body design will always have the edge over TNW, but are there any specific areas where you think you can revisit your analysis from the point of view of unsteady aerodynamics?
For those, I think the question here is, my analysis is pretty much steady CFD, what I can, which is sunshine and roses, yes, and what improvements I would do to my study, maybe go into unsteady CFD to improve my study. The answer is obviously yes. There's much more work to do. Actually, I would like to tackle the low-speed aero first to look at takeoff and landing performance before I go to more the edge of the envelope, unsteady aerodynamics, that. But yes, I don't disagree. This is fully, steady state, fully turbulent solution So yes, we don't know, and I'm actually looking much forward to JetZero's demonstration so that hopefully they can share some data in the public domain that I can hang my hat on. So,
Good.
One last question for Nick Borg, my buddy back there.
I'll just yell.
Yes.
Nick Warren has one quick question on the link list. A lot of times it's set by stall characteristics and not by cruise. So did you put any heuristics in the link list for the BWB? Because there was a pretty big delta in the initial final documents.
I will have to double check, but I do remember both Christian and Jay say yes, they put a limit on the stall to make sure that it's not stalled. Yes. That was an easy question.
Okay.
Thank you so much.
Let's thank the speakers again. Thank you.